Hey, Professor.
Hey, Amy. How's it going?
Sorry. Good. Just got out of vibrations.
Hmm. Who do you have for vibrations?
I have Dr. Sanders.
Oh, okay. How's that going so far?
So far, really good. I know he doesn't usually teach it, does he?
Not that I'm aware of. I don't know if this is his first time, but it is up his alley though. I mean, he's at least from what I know of his research interests.
Oh, all of you guys are full of surprises. It's pretty cool. I'll be right back.
Okay.
Buzzer.
Hey.
Is the notes today different than the ones you have up on Canvas? Just because
Let me
like the
see.
first slide, it has like 5 learning objectives instead of 4.
Oh yeah, because usually I can't fit all of the learning objectives here, so I usually just write a small subset of them. And so the ones that are in the lecture notes, those are a little bit more comprehensive. But for the lectures, I usually just write kind of the main ones.
Oh, okay, cool. Thank you.
Mm-hmm. bathroom real quick. Okay, it's 5:30, so let's go ahead and get started today. All right, good evening, everybody. Welcome to our second lecture for EGME 417. So how's everyone doing this evening?
Good.
Good, good, great. Yeah, it's first week. Everyone's still happy, so it's good. Maybe not so in a few weeks, but for now, you know, everyone's good. Okay, so you notice I've changed platforms here. So instead of doing PowerPoint, I'm now on my iPad. So you can't see it just from my webcam, but then I have an iPad in front of me right now. So this is basically kind of to emulate the in-class experience of writing on a whiteboard. Okay, so this will be kind of the usual thing. So usually when you come in, to the lecture, you'll see the learning objectives, which I've written on this iPad here. Okay. And so the plan for today is to go through the lecture notes 01, which are posted online. And this is kind of the introduction to a little bit of review of fluids and heat transfer, although you'll be surprised, we don't actually need that much review, but also just kind of talking more in depth about, what is computational engineering and what are some key concepts that are going to be with us throughout the rest of the class. Okay. Okay. So before I get rolling today, are there any questions that I can answer? Okay. So there's any questions at any time, definitely, feel free to ask. But if not, let's get going. Okay. So today, it's kind of a mix of a lot of different things. I mean, first of all, we're going to do, a little bit more introduction to the class, because there's some more ideas that I want to cover. We're going to do a little bit of review of heat transfer and fluids, although maybe not in the way that you would think. But it's kind of in a way to set us up for the rest of the class. And then we'll go over kind of some more general stuff too. Okay. All right. So first, let's talk just generally about just computational engineering. All right. So when I say computational engineering, what do I mean by that? Okay. And so I think the first place to start is to say, just generally, computational or otherwise, what is the goal for any kind of engineering analysis? And so when we talk about engineering analysis, just to kind of put it in plain words, you want to basically predict or determine what will happen to a physical system when we do something to it. Okay. Or in other words, when we apply some kind of external effects. Okay. Okay. So a little bit of a long definition, but I think it's kind of general enough to use, for a lot of different things. Okay. And so in particular for this class, we're interested in fluid and thermal systems, right? And so these ones are particularly difficult to work with because the equations are complicated. It's a little bit hard to get intuition for them. So it can be really difficult to analyze these because the physics involved with them are complex, okay? And so some kind of examples of, that where, we can apply this kind of knowledge will be in things like HVAC, right? Right. So I think we talked about that last time. So that's heating, ventilation, and air conditioning. Okay. Another area could be like pipe flow. Right. Electronics, actually, surprisingly, there's a lot of thermal engineering that has to go into electronics too, because all electronics, they produce a bunch of heat, and we have to cool them. Okay. Right. And so in the design of ships, obviously, there's a lot of fluid mechanics that have to go into that. And of course, aerospace, just as a field, there's tons of thermal and fluids applications there too. Okay. And so the thing that all of these applications have in common is that, in order to properly design for these things, we need to know what's going to happen to them when we subject them to external forcing, right? And so, like, for instance, say like we have like an aerospace application, right? So if we apply some kind of velocity to our space shuttle, we want to see what's going to happen to the rest of the space shuttle, right? And in reality, for any kind of complex problem, that's going to be difficult to do, right? And so this, this idea of performing engineering analysis, it really starts to scale up with the complexity of the problem, okay? And so as engineers, there's several different ways that we can go about performing engineering analysis, okay? Okay. And so the first category that I'll talk about is analytical methods. Okay. And so these methods are probably the ones you're familiar with from your previous classes in like heat transfer or fluid mechanics. And so I call these pen and paper methods, or pencil and paper. Okay. And I call it that because basically in order to perform your analysis, you're going to solve the governing equations with a pencil and a paper. Okay. Okay. And so the nice thing about this is that, if you can do it, like if the problem is simple enough for you to, perform hand calculations, this is, really simple, it's really fast, and it's really inexpensive, right? Okay. But the downside to this is that it's limited to very simple situations. Okay? Right? Because if you remember from your previous classes, whenever you did do a calculation by hand, it had to be something really simple, like the geometry was fairly simple, the boundary conditions were really simple, just so that you could do it. Because anytime if you throw any kind of complexity in the geometry in there, it starts to become really, really hard, right? Okay, so that's the first kind of category of analysis that we'll do. Okay? And so the next category is experimental. Okay. And so you've probably had exposure to this method of doing problems in your lab classes. Okay, and so the experimental approach is basically just to run a physical test, or in other words, go and try it in the real world. Okay. Okay. And so, the experimental approach is basically saying there's no point in sitting around and arguing whether an egg is going to break when you drop it. You might as well just grab an egg from your fridge and drop it and see what's going to happen, right? And so the nice thing about the experimental approach is that it gives the best data. Okay, and what I mean by that is that there's no arguing about whether your experimental results were true or not, because it actually happened, right? There's no really arguing against that. So if you run an experiment and you show that something's going to happen, then there's no arguing against that. Okay? But the downside of doing experiments is that it can be pretty time consuming, and it can be expensive. Okay. And so that's a big deal when you're working in fields where it's expensive to build prototypes, right? And so let's take an example of like you're working for Boeing or something, right? And you're working on an airplane wing. Boeing's not going to build you an airplane wing just so that you can test out a new design, right? Because building an airplane wing, it takes a really long time, and maybe it spends like months in fabrication, and then you have to kind of wait all that time, and it's really expensive to get all the materials for it. Okay, and so experiments, when you can do them, they're really great, but it's just not practical in a lot of situations. Okay. All right. Are there any questions on this so far before I turn the page? Okay. All right. And so the third approach, which is going to be the focus of this class, is computational. Okay. And so in the computational approach, it's actually very similar to analytical, because we're going to start from the governing equations. Okay. Okay. Most of the time, these are partial differential equations, but instead of solving them by hand, we're going to use computers to solve them for us. Okay. Okay. And just like we talked about on Monday, this has the benefits because computers are really, really fast at performing, these calculations. Okay. And so the upside for this is that, we avoid having to put together a really expensive and time-consuming experiment. But because the computers are so powerful and they can run so many calculations, we can use these to handle very complex situations. Okay? Okay. And the cost part's really important because, to run a simulation, a lot of you guys are going to be using your personal computers to doing this. So it basically, you can almost think of it as the only cost was to pay for the electricity to power your computer during that simulation, which is, very small because for our class, we're only going to be running simulations that last at most maybe like 10 seconds or something like that. Okay. Okay. And so everything in this class, is going to fall into this third category right here. Okay. And so what we're going to do is we're going to take basically the equations for fluid mechanics and heat transfer, mostly heat transfer, and then put it in a way such that they can be solved for computers. Okay. Okay. Um, but as we'll see as we go along in this class, that it can be really tricky. And so it's not a simple matter of just taking a problem, just throwing it at a computer, right? You have to really set it up in a way such that the computer can really understand. Okay. And so, one thing that we'll talk about and that will be clear throughout this entire semester, that, your computer can be a really powerful tool for your engineering work. But, just like any tool, it can be really misused. Okay. And so, basically the overall goal for this class is to learn the best ways to get the most out of your computers and to get accurate results for heat and fluid simulations. Okay. Okay. And so that's a bit more background on computational engineering and at least how it sits within the context of other engineering, analysis methods. Now let's start reviewing a bit on heat and fluids. Okay. Okay. And so, the main things that I want to review from heat and fluids are their big governing equations. Okay. And so from heat transfer, basically the big equation that we're going to be working with is the heat equation. And then the analogous equation for fluid mechanics is Navier Stokes. Okay. All right. And so just because I know, I think fluids is actually a prereq for heat transfer. So you guys probably never had a semester where you saw both of these equations kind of side by side. But what I'm going to show you is that these equations are actually very, very similar to each other. So their structure is almost identical with kind of one small difference for Navier Stokes. So I'm going to write down both equations. And then we're going to, I'll define all the terms in the equations, and then we'll talk about how they're similar, okay? All right, so first let's start with the heat equation. Okay. And in particular, this is the 2D heat equation, and it's unsteady. Okay. All right, so the heat equation is given by the following. And so we have rho times Cp. Okay, so rho is the density and Cp is the heat capacity. Okay. Then we have the partial derivative of the temperature with respect to time. Plus u times dt dx. It's a little messy. Okay, plus v times dt dy. Okay, and so that's the partial derivative of t with respect to y. And I can't write that partial sign for some reason. Okay. my palms get sweaty really easily, so it's it kind of makes it tough to write on the iPad. Oh, and I know my writing on the iPad can be pretty messy. So if there's anything that's not clear, definitely let me know. And I'm always happy to kind of clarify these things. Okay. Then we have K, which is the thermal conductivity, times partial squared T over partial x squared plus partial squared T over partial y squared, plus Q dot. Okay. Oh yeah, that's maybe that's a good idea. Maybe I should wear long sleeves. It's my palm in particular that's a bit difficult. Okay. So after a lot of struggle, here's the heat equation. Okay, so let's define all the terms in this equation. Okay. All right. So first we have capital T, and so capital T here is temperature. Okay. Next we have rho, and so rho here is the density of the material. Okay. Cp here is specific heat. Okay. K is the thermal conductivity. Okay. And then Q, this represents any kind of thermal production. Okay. Yeah, my palms get sweaty, and but my knees don't get weak. So, okay. So this is our heat equation here. So I know it's a little bit kind of a lot to just kind of start with a big kind of scary equation like this. But you know, what we're going to do basically is we're going to break this down kind of term by term and kind of explain what each of them mean. Okay. But before we do that, I'm going to write out the Navier Stokes equations, which I'm going to do on the next page. Okay. But so far, are there any questions on this? Okay. All right, so then now let's do Navier Stokes, and let's hope that this is a little bit more successful. Okay. Right. And so if you remember from your fluids class, Navier Stokes represents the conservation of mass and momentum for a fluid. Okay. And so again, this is going to be the 2D Navier Stokes, and it's going to be unsteady. Okay. Okay. All right. And so Navier Stokes looks like this. So we have rho, which is again our density. And we have partial U partial T plus U partial U partial X plus V partial U partial Y. And this is equal to minus dP dx, which is our pressure term, plus mu d squared U dx squared plus d squared u dy squared plus rho g. Okay. Yeah, so we're going to steer away from 3D simulations in this class. So we're going to mostly focus on 2D. But you know, you can extend a lot of these methods to 3D actually. And if anyone's interested later in the class, we can discuss that. But for the majority of this class, we're going to focus on 2D. Yeah. Okay. So let's go ahead and do the same. So let's define these terms. Okay. And so u, this is our x velocity. V is our y velocity. Okay. This P is our pressure. Let's see. Rho is the density like it was before. This symbol right here, this is our viscosity. And then G is gravity. Okay. So that's our Navier Stokes, right? All right, so we have two very intimidating equations, right? So we have our heat equation and we have the Navier Stokes, right? Probably you wouldn't ever think to see both of them in the same place like this. But what I'm going to argue to you guys is that these guys are almost the same equations. Okay? Okay. And so that's why we can kind of group these guys together because they're almost the same. Okay. Were they derived together? They're kind of derived in similar ways. So to get the heat equation, you derive that from conservation of energy, and then Navier Stokes you derive it from conservation of momentum. But the ideas are similar, it's just you apply different physical laws. Okay. And so to kind of show you that these guys are similar, let's take it kind of term by term. So I know I don't have the heat equation on here, but I'm going to basically go term by term here and circle them here. Okay? And so first, let's take a look at the first term in each of these equations. Okay. And so if you notice in both the heat equation and Navier Stokes, we have a term that has a derivative with respect to time. Okay. And so these guys are basically the same thing, and they represent what's called unsteadiness. Okay. Maybe it's just this red color that kind of hates me. Okay. Right, and so this is our partial t, and partial u, partial t. Okay. Okay, and so physically what these terms represent is that they represent the fact that our quantity of interest, which can either be temperature or velocity, can change with time at a fixed location. Okay. Okay. And so if you look at both the heat equation and Navier Stokes, that's basically the only part of the equation where time factors in. Okay. And so it kind of makes sense that both of these terms kind of serve the same purpose. Okay. All right. And so now let's look at these groups of terms right here. Okay. And so in Navier Stokes, we have u times du dx plus v du dy. And then in the heat equation, we have something similar. And so we have u dt dx plus v dt dy. Okay. And so these terms right here that I've circled in green, these represent what's called convection. Okay. And so with convection, notice a key part of this is that, you know, we have u and v in here, okay, in both the Navier Stokes equations and in the heat equation. Okay. And remember, U and V are the fluid velocities. Okay? And so what the convection term represents is the fact that our quantity of interest can be transported via a moving fluid. Okay? Okay. And so in the heat equation, this basically represents how temperature or energy, if you put it inside a moving fluid stream, it's going to transport with the stream. Okay. With Navier Stokes, it's a little bit weird because we have velocity that's transporting velocity, but that actually is true too. So the flowing fluid can also transport its own momentum. Okay. Okay. And now let's look at the second derivative terms. Okay. Okay. And so let's look at these guys for Navier Stokes, and then these guys for the heat equation right here. Okay. And so both the heat equation and Navier Stokes have a term where they have the second derivatives of our quantity of interest added to each other in each direction. Okay. And so what these terms represent here, these represent diffusion. Okay. And so physically, what diffusion represents is passive spreading of a quantity in a medium. Okay. Okay. And so in both the heat equation and in Navier Stokes, we have passive spreading. Okay. And so what this means basically is that, if you sit or if you, don't put a moving fluid or anything, then either both the temperature and the momentum, is going to spread passively, right? And so intuitively, you can think of diffusion as like, say, you're sitting in your chair, and then let's say you fart or something, right? And so even if there's no air that's flowing in your room, eventually that fart is going to get to all the corners of the room, right? Just by kind of passive spreading. And so that process of passive spreading is called diffusion. Okay. And so both the heat equation and Navier Stokes have a diffusion term. And now let's look at this kind of extra guy over here. Okay. And so on Navier Stokes, we have the density times gravity. And this is kind of the same thing as this Q dot right here, which represented thermal production, right? And so even though these guys seem physically like they're very different things, mathematically, they do kind of the same thing to the equations, okay? And so these terms right here, which are, you can kind of almost think of them as like extra terms, because they don't have, a variable that's associated with them. Like there's no temperature and there's no velocity in them. Both of these terms are classified as source terms. Okay. Right. And basically, both of these represent a way for our quantity of interest to be spontaneously generated within the medium. Okay. Okay. And so, this, I think this physically, this term is a little bit, is the most difficult to understand, but let's think of just Navier Stokes for a second. Okay. And so Navier Stokes, basically what it's saying is that gravity can kind of spontaneously cause it to build up momentum. Okay. And so one way that you can test this is that you say you have a glass of water. This is empty right now, right? And then let's say you pour it out, right? And so in other words, you're not really putting any forcing on that fluid. The only thing that's forcing the fluid is gravity, right? And so because gravity is acting on the fluid is kind of spontaneously gaining momentum because it's falling through the gravity field, okay? And so, equations like these, they have a way, they include this term here for any kind of external effects that can produce, spontaneous stuff, okay? And in the heat equation, we represent this with thermal production. So maybe you have like a heat pack or something like that, and some chemical reactions within the heat pack are producing heat, right? It's basically converting chemical energy into thermal energy. Okay. And so those terms kind of represent kind of the same thing. And then one last term that we have here. This is the thing that kind of makes Navier Stokes unique, is that we also have this pressure term. Okay. And so there's nothing like this in the heat equation. So this is something that's unique to Navier Stokes. And so this is what kind of makes it almost the same. Okay. And all the pressure term kind of represents is that, pressure is just another force that can be used to drive fluid motion. Okay. But that's unique to fluid. So we're not going to focus on it too much unless we kind of get into CFD later in the class. Okay. Okay. Are there any questions on this so far? Yeah, so I know it's. Oh, go ahead.
Can you explain what the source is again?
Yeah.
Regarding the glass of water.
Yeah. So the glass of water, say probably a better analogy is if you kind of held water in your hand and you kind of just let it go, right? And so because normally, if you consider an object and you want to give it momentum, you have to push it, right? You have to put a force on it. But because of gravity, you can just let it go and you don't have to do anything else. And then the water will have momentum as it falls down, right? And so, yeah, exactly like a waterfall. And so a source term basically represents how, there's other things that can spontaneously kind of give your objects, or in this case, your fluid, momentum. And for the thermal case, one way that you can do that is to perform a chemical reaction, right? And so if you think of the way like heat packs work, so heat packs basically transform chemical energy by producing, chemical reactions, and it turns that into heat. Yeah. Does that make it a bit more clear?
Yes, thank you.
Yeah, we'll revisit this. So we'll be seeing these equations for for the whole class, and you guys will be sick of them. So we'll be revisiting this kind of over and over and over again for this class. Yeah. Okay. Any more questions on this page here? Okay. All right. So I spent a lot of time talking about each of those different terms because your physical intuition or your physical understanding of them will be really important as we go about writing the code for these. Okay. Because basically how this class is going to go is that we're going to visit each of these four terms kind of individually, and then we're going to see how we can write code to actually simulate them accurately. Okay. And so in order to kind of check your simulation results, you should kind of have some physical intuition for what those terms represent, so that you can write your code, get your results, and think, does this kind of make sense to me? Kind of based on what I physically expect this to do. Okay. Like for instance, we're going to start with diffusion, because diffusion is kind of the simplest one to do. And so what you'll see from all our diffusion equations or our diffusion solutions, you should see kind of a passive kind of spreading of our solution. Okay. And so I really want you guys to kind of keep these kind of physical understandings and really anchor it into your mind. Okay. Okay. And so the only exception for this is pressure, because pressure, I don't know if we're going to get if we're going to be able to learn too much about the theory behind CFD, but we might work with some commercial code. So, but if we do have a CFD class, you'll see that the pressure term is like kind of a bitch to simulate. So it kind of messes a lot of things up, and that's the term that makes CFD really difficult. But because we're ignoring pressure, we can kind of work with a simpler equation. Right? And so with that in mind, for the rest of this class, I'm gonna work with what I call the generalized conservation equation. Okay. And so because we've just seen that both the heat equation and Navier Stokes look the same, or at least they have a lot of similarities, we can kind of come up with a generalized equation that kind of encapsulates both of them, that has all of the all of the terms and all the behaviors that we expect. Okay. And so instead of using t and instead of using velocity, I'm going to use just a general variable called phi. Okay. And I use phi just because it's a little bit clear. It's a little bit clearer, and it's a little bit easier to write. Okay? And so our general conservation equation is going to look like this. Okay. Okay. Right. And so you can see from the from this expression that we have all of the all the main components. Okay. And so we have here our time derivative. So this is our unsteady term. Okay. Here we have our convection terms. Okay. Here we have our diffusion terms. I think I used purple for it. Let me start blue. Okay. Okay. And finally, we have our source. Okay. Okay. And so from here on in the class, I'm going to use this conservation equation instead of the heat equation or Navier Stokes. Okay. But if you just replace phi with t and you replace this gamma right here with k, then this is basically exactly the heat equation. Okay. Actually, one other thing that you can use this equation for is actually to simulate mass transfer, believe it or not. So actually the mass transfer equation uses this exact same equation. And so that's why, this equation is so general and it's so useful, because it can be used for, so many different phenomena, for heat transfer, for mass transfer, and for fluids as well. Okay. And so just like, I mentioned before, we're going to take this equation and kind of work with it kind of term by term. And then we'll see, how we can write the code to actually simulate each of these phenomena. Okay. And then as we go through the semester, and as we learn how to simulate each one, we'll kind of add those codes to each other. And then eventually we'll be able to simulate this entire equation. Okay. Okay. So I know it's kind of a scary partial differential equation now, but we'll go through it kind of week by week, and then it'll be a little bit less scary. Okay. Any questions on this?
Professor?
Yeah.
What's the R term for the diffusion? That circle that's that's being multiplied.
Yeah. So this
for that equation.
This right here is gamma. So it kind of looks like a hangman. Okay.
Thank you.
Yeah. So in general, this is basically just a diffusion constant. So this is kind of the same thing as your thermal conductivity or your viscosity. But yeah, I just generalize it here for as just a general diffusion constant. Yeah. Good observation. Okay. And so that's our general conservation equation. And so that's all you kind of have to remember from heat and for fluid. So the only thing you need to know is just you need to remember that there was a heat equation and then there was Navier Stokes, and here they are again. And then from here, we can go from here. Okay. All right. So let's talk about kind of the process on which we need to do to actually run a simulation. Okay. So I call this the discretization process. And so, in order for a computer to actually solve this problem, we need to put it in a different form because a computer actually doesn't understand partial differential equations at all. Okay, and so the process of taking a physical problem and then putting it in a form that a computer can solve, that's called discretization. Okay. Okay. And there's several steps that constitute this process. Okay. And so there's basically 4 steps that we're going to go over. Okay. So let me start on the next page. Okay, so the first step in the discretization process is to simply just define the problem domain and all the relevant physics. Okay. And so what I mean by this is to first establish your geometry. Okay. Okay. And so do you want to solve, do you want to compute something on a turbine? Do you want to work on an engine, on an airplane wing? You first kind of have to define, what your problem geometry is going to be. So this part is usually automatic. And so, usually you have a CAD file or you have, a problem that you already have in mind. So, but, it is an explicit part of the process to actually define where you want to, run your simulation on. Okay. And then by defining your physics, you need to determine whether this is going to be a fluids problem, whether it's going to be a heat problem, whether it's going to be combined. So a lot of times, you're going to run both a heat and a fluid simulations at the same time. Okay. Because depending on which fluids are relevant, that's going to change, which equations that you're going to use to solve, right? And so, schematically, let's draw just a figure to kind of show this, okay? And so, your problem geometry obviously can be, very complex, but for this, I'm just going to use a potato, okay? Okay. And so there's our problem domain. And so usually the domain is given the symbol omega, okay? And then, let's say that we want to solve the heat equation on this, okay? Okay. And at this point, you can also apply some assumptions to simplify this. So let's say that, we're going to solve this in steady state. So in steady state, we can cancel out this guy. Okay. And let's say that we also know that there's going to be no source. Okay. Because even though the computer, can solve really difficult problems, if you can simplify the equations before you give it to the computer, that's actually going to be worth a lot of times too. Okay. Okay. Another thing you have to define at this point is you have to define your boundary conditions. Okay. And so what boundary conditions are is they express how the solution is going to behave at the boundaries of your domain. Okay. Cool. Okay. So that's a really important part, because this governing equation will only be able to solve for on kind of the interior of the domain, but we also need the boundary conditions to define how that's going to be, how the solution is going to act on the boundaries, and that actually makes like a really big difference on the solution as well. Okay. So any questions on this? Okay. All right, so that's step one. So step one is kind of defining defining all the aspects of your problem. So geometry, physics, and boundary conditions. And so, step one actually isn't unique to just discretization. So even if you're going to perform an experiment or solve this by hand, you would perform step one anyway. So step one is just kind of good engineering, just defining your problem. Okay. All right. So step two is where we actually start to discretize. Okay. And so the first thing we need to discretize is the domain. Okay? So I call this domain discretization. Okay. And the point of this step is to take your geometry and then break it up into a lot of simpler shapes. Okay? Okay. And so the reason we do this is that most geometries are pretty complex, and it's even hard for a computer to take just a big complex object and to solve some physics on it. And so to kind of make it simpler for the computer, we have to take our geometry and break it up into a lot of simpler shapes. Okay. Right. So so visually, it'll at least for this class, it'll look like we're putting a grid on top. Okay. Okay. Or another popular name for this that's used a lot is meshing. Okay. And so visually it looks something like this. So let's say that we have this is our original geometry. Okay. And then after we mesh it, it's going to look something like this. Okay. And so we've taken, now it looks kind of like a waffle, I guess. But now we've taken this thing that looked like a potato, and now we've made it into a bunch of little squares, right? Okay. And because, you know, we've broken it up and each square basically looks the same as the next one, you know, this is going to be a lot easier for the computer to solve. Yeah. Yeah, it looks like a waffle. Yep. And actually, you know, this step is actually really important for running simulations because, you know, you have a lot of decisions on how fine or how coarse you want to make your mesh. Okay, and so you can either make a coarse mesh or a fine mesh. Okay? And so coarse mesh might look something like this. And so coarse mesh, you know, has relatively small a small amount of shapes, whereas a fine mesh, you know, has a lot of these little simple shapes. Okay. And so the analogy that I like to use with meshing is think of like, you know, the pixels on an image, right? And so for some images, in order to save space, you can kind of pixelate it and turn it in lower quality, right? And so that's going to be your coarse mesh. So your coarse mesh, typically these simulations tend to be a lot faster because your mesh doesn't have that many elements in it, okay? But your accuracy might not be that good. Or you can use a fine mesh where, you know, you put a really fine grid on it, and your simulation is going to take, you know, a little bit longer. It's going to take more memory to accomplish, but you're going to get a much more accurate solution. Okay, and we'll talk a bit about, you know, accuracy kind of after this. But are there any questions on domain discretization? Now I'm hungry too. Okay. And so that's domain discretization. And so that's an important part. And so the next part, actually, this is where we're going to spend most of this class. The next part is to actually discretize the equations. Okay. Okay. And so this process right here is to basically take our differential equation and turn it into an algebraic one. Okay. And the reason, you know, this might seem like a really silly step, but the reason we do this is that computers, you know, the way that they're kind of set up is they're really, really good at performing linear algebra. Okay. And so if you can set up a problem to look like a linear algebra problem for a computer, the computer's basically got your back, so it can solve that no problem. Okay. Okay. And so we'll start talking about this, you know, near the end of next week. But basically, we're going to take all of our derivatives and turn them into algebraic expressions. Okay. And so, just as an example, you might take a derivative like this, and you might turn it into kind of an arithmetic expression that looks like something like this. Okay. And so on the left side, we have a derivative, which the computer has no idea what to do with it. And on the right side, we have basically an arithmetic or algebraic expression, which is good. Okay. And so by doing this, by discretizing the equations and then applying that to our grid or to our last step, we're going to end up with a really big system of linear equations. And so we're going to have a system of, maybe several hundred equations and several hundred unknowns. Okay. And so a lot of this class will be focused on this step here. So we're gonna learn two different techniques for doing this. And so the first technique is called finite difference, okay, which will be kind of the first thing that we do in the class. And then the other technique is, which we'll learn later, is called finite volume. Okay. Okay. And so that's where most of the theory and most of your coding is going to come into play. Okay. And so once you're done with that, and you've set up this kind of gigantic linear system, the only thing left to do now is to solve. Okay. Okay. And so basically you're going to have a large coefficient matrix, a large coefficient vector, and you're basically going to solve them. Okay. And so it's going to look something like this. And so let's say that we have a large matrix A, a vector X, and this is going to equal to some vector B. Okay. And then to solve this, we can just do X is equal to A inverse B. And so, yeah, actually this part, we're actually going to let the computer do this because at this point, we've set up the problem really well. And so now the computer can kind of take over from here and solve this problem. Okay. And so step 4, usually this is the part where, it would take a really long time to solve, but this is where the computer comes in and really does all the heavy lifting for you. Okay. And so step 4 for us is really simple because it's usually just one line of code just to tell the computer to solve. But this is where the computer kind of does its work and kind of makes its money. Okay. Okay. And so for the rest of the semester, we're going to basically be following this 4-step process right here. Again, spending most of our time on step number 3. Okay. All right. Any questions on this? Okay. All right, so there's one more concept I want to go over before we sign off for today, and it's just kind of general concepts of approximation, error, and convergence. Okay. Okay. And so even though we're going to be learning all these computational techniques, I want you guys to always remember that computations is always going to be an approximate technique. Okay. In other words, what this means is that no matter how good your code is and no matter how well you set up the problem, there's always going to be a difference between what you simulate and what actually happens in reality. Okay. Okay. And so, of course, we often want this difference to be really small. And, a lot of times if we set it up properly, this difference is really small. But, there always is going to be that difference. Okay. All right. So question in the chat, you mean because of 32-bit and 64-bit sizes, that actually does contribute to it a little bit. So that's one contributing factor. But there's a bunch of other factors too, just the fact that, we're using equations to represent complex physical phenomena too. Okay. So the question is, what accuracy are we looking for? So, of course we want the most accuracy as possible. But, a lot of times we don't know exactly how that's going to be. Because a lot of times it's a little bit hard to verify, because in order to really verify, how accurate your simulation is, you need to recreate basically the exact same situation in reality, and then kind of compare those two. Okay. But sometimes we can. Okay. And so, I want to make a definition here. And so we can define the error in our simulations to be this difference between our simulation results and reality. Okay. Okay. And so we have error is equal to simulation minus reality. Okay. And so one example of this is, let's say that you ran a thermal simulation of the temperature distribution in a plate or something, right? And then you did that exact same experiment, and you measured the temperature at a specific location, let's say at the tip of the plate. Okay. And so the error in your simulation is just going to be whatever difference between what you simulate and what you actually measure. Okay. And so what we hope, and if you set up your simulation properly, this error is going to be really small, like maybe 0.0000000001. That might be the difference. But I want you guys to always be aware that there is always going to be a difference, because the simulation is not reality. Unless we are living in a giant simulation. But that's a conversation for another day. Okay. And there's a lot of things that we can do with our simulation to kind of control how accurate our simulation is going to be. Okay. And so in step 2 of our discretization process, we talked about coarse and fine meshes. Okay. Let's see. It's always this part of my iPad that's hard to write on. Yeah. Okay. And so let me draw kind of 2 examples again. And so let's say that we have a coarse mesh. Right? Okay. And so, I use the word coarse because, if you're familiar with kind of sand or like salt, right? Coarse, when you talk about coarse grains, you're talking about grains that are fairly large, right? And so here, when we say a coarse grid or a coarse mesh, the elements themselves are pretty large, okay? Versus, a fine mesh, which may look something like this. Okay. Generally, we assume, or generally what tends to happen is that for a finer mesh like this, the error tends to be lower for these ones. It's like looking at a computer image, right? So generally you expect a higher resolution image with more pixels to be a more accurate representation of reality, right? None of that pixelated JPEG crap, right? So maybe something high quality like 4K, right? And so a 4K image is always going to look better. You know, Costco's never going to put like a JPEG in front of their on their big screens when you walk in, right? It's always going to be a very beautiful 4K image with 4K pixels, right? And so it's the same thing for simulation. So the more fine your grid is, the more elements, the more grid points, the more edges that are in your domain discretization, the more accurate your simulation is going to be. Okay. Any questions on this?
Is there like a rule of thumb that you want to use when you're applying a mesh, like on a complex geometry?
Yeah, no, that's a great question, and I think that's the one issue that I think haunts everyone. Unfortunately, you know, there's the mesh that you need to get, you know, a sufficiently accurate answer. Unfortunately, it's very problem specific, and so there's no kind of hard answer for it. You know, eventually, you know, as you run, you know, as you get kind of used to the field, you kind of get an eye for, you know, this mesh looks good and this mesh does not look good. But that kind of takes a lot of experience to do. But even, you know, once you do get good at that, one thing that needs to be done, no matter what, you know, anytime you do a computational study, is you need to do what's called a mesh convergence test. And so what that means is that you run your simulation on different grids or different meshes with different, you know, different number of density. And so you might start with something coarse and you go to something fine. And then what you should be able to show is that as you refine your mesh, once you get past a certain point, then your solution, there's no appreciable difference. So there's like less than a 0.1% difference in your solution as you go from, you know, this mesh to a finer mesh. And if you can prove that, and if you can show that, then that at least says that, you know, your mesh is the best that it can be for this particular problem. Yeah.
Got it. Thank you so much.
Mm-hmm. And actually, that brings me to my next point about convergence, which is another important term to define. And so convergence is the idea that, you know, you get increasing accuracy as your grid is defined, okay? Refined. Okay. And so as you put, you know, more and more elements or more and more grid points into your domain discretization, you should expect a more accurate solution. Okay. And so we use this term because we can say that as we refine our mesh, we're converging on the true and real solution. Okay. But unfortunately, you know, refinement isn't free. Question. Yes. There's a limit like an asymptote. Yeah, exactly. So it, basically, as you refine your mesh, you kind of asymptote towards the exact solution, or as close as you can to the exact solution. Okay. Okay. So the last point I want to leave you with is refinement isn't free. Right? Because if you just kind of read the last couple statements, you know, the fair question to ask is, why don't we just refine every single mesh such that they're all really refined, right? And so why can't all images on the internet be 4K, right? And the reason for that is, you know, as you refine some more, it's gonna incur some cost, right? Okay. And so what do I mean by cost, right? And so since we're going to be working in computers, you know, the most obvious cost is going to be in terms of memory, okay? because you not only have to store the grid itself, but you also have to store the solution at all the grid points, okay? Yes, and so Juan brought up a great point. So the next cost is just time. And so the more refined your grid is, or the more grid points there are going to be, it's going to take longer and longer for you to produce the solutions, okay? And so for a lot of the problems that we have in this class, maybe it doesn't seem like that big a deal. So like maybe you go from a 1 second simulation to an 8 second simulation. And so that might not seem like a big deal. But when you start to, do some really, really, complex problems, you could be looking at, days or weeks, or even I've seen some simulation run for months at a time too. So the time factor starts to become really relevant, once you start to get into really, really complicated stuff. Like one example that I know that always takes forever are simulations of turbulent flow, right? And so turbulent fluid flow is, I think, probably one of the most complex phenomenon that, that are out there right now in science. And so if you want to simulate turbulent fluid flow over, something large like an airplane, that is a chonker of a simulation that will take, first of all, it's going to take up, tons of computing cores. And so those simulations typically run on several thousand, computing cores, and it's going to take you, probably several weeks of your life to kind of wait for it. Yeah. So, time really becomes a factor for those really big ones. So you really want to be careful with that. Yeah. Yeah. So it's, we're not going to see most of that, for this class, because we're kind of learning the methods kind of from scratch. We're going to be dealing with a lot of, small and medium-sized problems. But once you get to kind of the really big problems, the time and the memory costs really start to be significant. So you can't just refine willy-nilly. You need to have kind of a plan for it and kind of a good reason to refine. And you should only go up to a certain point. Yeah. All right, question. So what kind of software is used to run them chunk simulations? Yeah, so Kyle brought up a good one. So Star CCM is a very commonly used code. A lot of the like OpenFOAM is another one that uses that. So I'm going to try to see if we can work OpenFOAM into our class at the end, just so that you have some exposure to that. But yeah, there's Star CCM, I think, is probably one of the most common ones. Yeah. And so, yeah, so usually only in industry that you see those ones. So in this class, we're not going to do really big problems like that. Because in reality, we're going to be using MATLAB for this class mostly. I know some people have interest in Python. Python's a bit better, but MATLAB is not the fastest programming language out there. So there's a lot of limitations to what we can do in MATLAB. Yeah. Yeah, and Python's a bit better. ANSYS is pretty good, but in order to use ANSYS for big problems, you need to pay a lot of money for it. So ANSYS is good; it's just really expensive. Yeah, yeah. ANSYS takes a chunk of money to use it. Okay, and so it's past time, so it's 6:46. So I don't want to keep you guys, and so that's all I had planned for today. And so thank you everyone for tuning in. So I'll stick around after, if you guys have some more questions. But if not, you can go ahead and sign off. So thanks for tuning in. Have a great weekend, and I'll see you on Monday.
Thanks, Professor. Have a good
Thanks,
weekend.
guys. Thanks, you too.
Professor, do you mind going to page number 9 really quick, please?
Sure.
Thank you.
Oh yeah, Star CCM is a paid software too. Yeah, I forgot that. I knew a lot of people that had licenses for it in grad school. So to me, because I know a lot of people that use it, it seems cheap, but I forgot that you have to pay for it too.
Professor?
Yep. Mm-hmm.
Your notes are available on online, right?
Yes. Yeah. So both the lecture notes from Monday and for today are online. Mm-hmm.
And I forgot did you say you record your lectures too?
Yes. Yeah. So this it's recording right now. So I usually upload it to YouTube right after the class, and it'll be up before the end of today.
Oh, okay. Thank
Yeah,
you.
some of my old ones are there too, because last time I taught this was last spring, and then COVID kind of shut us down halfway. So the second half of the class is on YouTube from last year, but the first half is not, because that was still in person back at the time. Yeah. Yeah. Mm-hmm. Okay. Yeah, Dr. Banks, I guess, is doing recordings too. Mm-hmm.